All right, welcome back. It's my great pleasure to introduce my new colleague in my home department, computer science, Professor Liu. So Ray joined us just last fall, so he's very new here. So his research interest is in machine learning system, machine learning and graphs, and also, of course, general machine learning. And his recent research attention mostly focused on large language models, from what I see from his talks and publications. So Ray has regularly published in the top machine learning places and also machine learning system places. And I think one remarkable thing about his research is the real world impact his work has is actually adopted in multiple famous places like Paris, high-increase transformer, and also featured in Go Campus. So without further ado, let's welcome Ray to give us his recent research on how to make large language models to work with large context. Welcome, Ray.
Yes, thank you for the kind introduction. Yes, today we will talk about some of my recent work done last year about advancing the context length or making the large language model can process longer input better. Okay, so let's start. I will first briefly introduce the concept of long context. Actually, the problem of long context is conceptually very simple. Basically, refer to you feed a super long piece of information into the model, and let the model to do some understanding or answer, for example, answer some questions with respect to this given concept, with respect to this given context. So here, for example, imagine we feed the entire code repo of PyTorch into a chatbot, and we ask it some question like how to fix this issue. Okay, what should I do if I have the out of memory errors? So something like that. So besides the coding scenario, we can also, for example, feed like a super long article into it, like financial report of a company. And or we can even feed two company financial report and ask the chatbot, okay, which one is financially stronger? Okay, something like that. That all refer to the long context scenario. Okay, so we can see long context naturally have lots of the applications in real world. But here I want to mention two more very important scenarios regarding long context. The first one is customization. Okay, so I will first talk about how we build a healthcare agent from a pre-trained language model. So for example, imagine we have a llama, for example, because llama is llama barely know about like domain-specific medical knowledge. So here I will talk about the procedure of building a healthcare agent from a pre-trained one. Well, just like I previously mentioned, so llama, they barely know about anything regarding a domain-specific language like medical domain. So the first thing you need to do is something called continuous pre-train. So continuous pre-training is a rarely used word compared to the common training phase like pre-training and fine-tuning. But in practice, if we really want to build a domain-specific chatbot, continuous pre-train is inevitable. Okay, so the difference between continuous pre-train and fine-tuning is that you got more data in the continuous pre-train, much more data compared to the fine-tuning scenario. So basically, continuous pre-training is a stage between pre-training and fine-tuning. So in order to inject knowledge, you must mix the domain-specific knowledge or domain-specific data with the original pre-trained data. So why you need to do data mixing is because if you do not do data mixing, they will forget what they learned during pre-training. Okay, so this part actually is pretty engineering. So it's really hard to determine what's the best ratio of mixing different domains. So it has a huge impact on the final performance. Okay, so basically after this stage, you build a chatbot that can remember remember the domain-specific knowledge. And the second stage we need to do is alignment. We need to do reinforcement learning from human feedback and also supervised fine-tuning. Basically, this stage is let the chatbot to align with the human doctor preference. You can think it this way. After alignment, the model learn to answer like a doctor. So they learn to give answer that is most helpful and faithful to the final users. And the third one is the fact check, but actually it is optional. You can have it or not. So, but in my opinion, it's good to have retrieval augmented generation. Basically, this stage is to let the model to do a fact check from a database, because the model may hallucinate or they may generate some unrelated answers with respect to the user queries. So for this stage, you can basically think, okay, every time the model generates the answer, they first search from the database and try to find related information from a database. So for example, in this case, PubMed. Okay, and then after collecting the relevant context with respect to the user queries, then they answer the questions based on the retrieval context. Okay, and finally, the last one, I call it in-context learning, but this stage they can have different name. So for example, in-context learning prompts engineering. So basically just refer to user feed the questions and their conditions into the chatbot and ask the related questions. So here we can see all retrieved files, they are injected into prompts. Okay, so they will enlarge the prompt length. This is the first thing. The second thing is that if we really want a customized answer, we need to feed more information into it. So you can imagine the more of the customization level, the longer the context length. Okay, and another thing I want to mention is that all patient information or all user information, they should be only used during the in-context learning, or they should only be fed into as the prompt. They should not, for example, use it during the continuous pre-training and fine-tuning. The reason is pretty simple. If you fine-tune the user data in these two stages, it is very easy for other people to extract this piece of information. That is really bad. So the information in prompt is something like you use it and then you drop it. Okay, so it's much safer. So the first observation is that the prompt length scale with the customization level. So you can imagine if you want a super detailed answer that tailored to your own conditions, you probably need to feed lots of the information. Okay. The second one I think is really interesting. It is the reasoning scenario. I know that recently DeepSeek they got lots of they attract lots of attention from the entire community. So, but the reasoning in a short term is that the reasoning enable the model to think before answer. So here I show some results of my benchmark, some of the representative example of comparing DeepSeek model and original model. So here, so for example, if you ask the model one mathematical question, so here for example, how many positive whole number divisors does 196 have? Okay, if you use original model, Llama 3.3 70 billion models. So they are still this base model actually is very good. They can reason step by step and give you the final correct answer. The final answer is 9. But here you can see this is if you augment the base model with the DeepSeek reasoning data. So by reasoning data is mainly referred to the data with complex reasoning trees. If you detail the model on the DeepSeek generated data, so the model can learn the reasoning pattern of DeepSeek model. So here, this is what happens after you distillation. The model can still give you a correct answer, but later they learn to do a fact check or they learn to do self-correct. Okay, so they learn to verify whether its answer is correct or not, and they will repeat this process again and again until they think, okay, this answer is correct. So you can see, so the reasoning augmented data is really, they can really get a super long output length. So this is very different to previous scenario. So in before reasoning model, before the popularity of the reasoning model, we mainly have the long input, short output scenario. But from the reasoning scenario, we know actually more in area of long output. We can either have short output, we can either have short input, long output, or long input, long output. So that being said, the reasoning model really increase the context length by a lot. So by combining the previously mentioned two motivations, the context length of language model is a fundamental container of complex behavior like reasoning, customization, or planning. If you, for example, if you want to build a agent or multi-agent, reasoning and planning ability is very important. Okay, but in practice, actually, the context length of a model is limited by two factors. The first one is that language model actually they cannot do the inference when your serving length is longer than the length you used during pre-training. This is the first limitation. The second limitation is that the serving memory grows with the length. Okay, the longer your input, the larger the memory you need to do the inference. Okay. So let's first talk about the first challenge. LLM or any transformers, they cannot generalize when the serving length is longer than the pre-trained length. So the root cause of this problem is again very simple, because of the out of distribution issues. So here, for example, for this model, 2000, this line is the original pre-trained length. So you can see during pre-training, you only see the position from 0 to 2000. But if you do an inference on, for example, on a sentence with 4,000 words, there are the position from 2000 to 4,000. They are all out of distribution for a pre-trained model because they never seen these positions during pre-training. So you can see this can drive the attention logic really go to crazy or even unreasonable numbers. So sorry, like crazy numbers. So here you can see for all attention logics, by attention logic is referred to the raw attention score before the softmax. So you can see the in-distribution attention logic is very normal. So they are very close to 0 compared to these crazy values. But right after the pre-trained length, you can see attention logic, they can get really crazy and they can grow up to even 8,000, which is magnitude large. It is many magnitude of larger than the normal values that will basically drive your model to only output nonsense output. Okay, the second challenge is that LLM, they need to cache all intermediate states of all tokens. Actually, this thing not only applied to large language model, it actually applied to any autoregressive model. So if you are doing autoregressive inference, you have this one, you have the KV cache or intermediate state. So LLM or any autoregressive model, they need to cache intermediate state of each tokens. And the KV cache, so this thing in the transformer inference context is often called KV cache. Okay, the KV cache, they grow with the context length, and they will become the new bottleneck compared to the model weight. So here, so for example, if you ask a model a short questions, like a question with only 500 words, you can see the model weight takes the majority of the memory, almost 98%. But if you increase your questions length to 100,000, like what I mentioned in the first slide, you feed the entire code ripple of PyTorch into the model. This will happen. Okay, so in this case, the KV cache take 80% of the total memories, which is much larger than the model itself. So you can imagine if you further increase the sequence length, like you are doing, like previously mentioned, you are doing reasoning over a long, lengthy article. So the sequence length will become longer than 1 million, and in that case, the entire memory is taken by KV cache. So actually, this thing not only applied to the pure natural language processing model, it also applies to multimodal model. Like if you are doing video generation, long video understanding, you can imagine the KV cache will really crazy because your video can get super long in practice.
A quick question here. So why we need to do this cache? So my understanding, this is like we're doing inference, right?
Yeah.
Why we need to do the cache of the intermediate result?
Yeah. Very, very good questions. So this is actually a trick for trading of memory for improving speed. So because in self-attention mechanism, you need to explicitly calculate the pairwise attention score, right? So if you so for example, every time you just increase one word or you just add one word to this attention matrix. So if you do not catch the all previous token, you need to repeatedly calculate the n by n matrix, which is really bad. They will significantly slow down your inference process. So one smart idea is that you just catch the k and v of all previous token, and you just calculate the new token with respect the new attention score of the new token with respect to the catch the k and v. In this way, you avoid recalculating the all previous pairwise interaction score. So that's
I see. So we are talking about the tokens in the same sequence, right? So if I have my sequence considered, let's say 100 tokens.
Yeah.
I would, because there's a sequential relationship, I should try to store the earlier ones. So
yes.
I see.
I can give you a quick illustration of why this happens.
Okay.
So imagine you have a 3 by 3 attention matrix. So this is word 1, word 2, and word 3. And next time you add one new word because they are doing autoregressive, right? So you have one word 4. The word 4 is a new word. So you basically make this matrix grow by one row and one column. But all this part is actually repeated. So you do not want to recalculate this thing. So a better idea is that you just calculate the k of word 1, 2, 3, and you just catch the word 1, 2, 3 and v of word 1, 2, 3, and you just calculate this row. So in order to calculate this row, you just use the query of the fourth word and multiply with them, and then you just calculate this new row. That's why you need to do a KV cache.
People will clean this up after, let's say I now have a new query. People clean this up, right?
They can be free.
Okay.
So now let's talk about the 3 work I'm gonna talk in this seminar. The first one is self-extend, which is a tuning-free extension work to enlarge the serving length to deal with the first challenge, the challenge that the language model they cannot serve with a length longer than pre-trained length. The second work is a KV cache compression work. So basically lower the numerical position of KV cache, so such that you can hold more number of requests simultaneously and have a faster inference speed. And third one is some benchmark regarding comparing Mamba and the transformers, okay? Because Mamba is originally developed for the long context scenario. Okay, let's further talk about the first one. So recall that previously I mentioned large language model or the large language model, they fail when the serving length is longer than pre-trained length because they have many unseen positions during the inference. So here is more details regarding the position embedding which used in large language model. Actually, they are using something called rotary position embedding or relative position embedding. So here you can see in this attention distance matrix, every number refer to the distance of the word order. So here, for example, imagine on the original input is allow machine learning, and the relative position distance between the word love and the word machine is 1. So we have 1 in this distance matrix. So this applies to all different pair of words. So the problem is that if the serving length is longer than pre-trained length, that means we have some never seen relative distance. So here, for example, imagine the original pre-trained context window is 5. So that being said, you train the model on sentence with only 5 words during pre-training. But imagine if you do a inference on a sentence with 8 words, this is what gonna happen. So the relative position marked by orange color, they are all in distribution because they have been seen during the pre-training. But for the position 5, 6, 7, they are never seen during pre-training. So that being said, they will cause the out of distribution problem. So the out of distribution problem drives the attention logic crazy. And basically, if you have this attention score, this is actually attention logic. So if you have this attention logic, basically model cannot output any make sense output. So one simple way to deal with this problem is that we can enlarge the pre-trained length, right? So basically, so for example, if we increase the pre-trained length from 8,000 towards 32,000, then we can increase the pre-trained length to, we can improve the effective context length to 32,000. But in practice, this method is really hard for 2 reasons. First one is that self-attention computation scale quadratically with respect to length, because you need to explicitly calculate the pairwise attention score, which is in size of n squared. N here is the number of words. So that's really bad. The second thing is, and actually I think the second reason is a key reason. Natural long context data is actually very limited in practice. So it's very hard for people to collect a huge number of high quality pre-trained data to do pre-training. So here I want to mention one more thing, that actually this work was done for at the stage of Llama 2. Actually, for Llama 3.1, they grow the length from 8,000 to 128,000. They do this by further enlarge the pre-trained length from 8,000 to 128 by splitting the continuous pre-training to 6 or 8 edges. At different stages, they use different context lengths to gradually increase the context length. Okay, so this slide is a little bit out of date, to be honest. Okay. So here we gonna talk about our key idea on how we deal with this problem. So actually, our key idea is very simple. So out of distribution cause this problem. So one idea to deal with this issue is that we can build a mapping to remap the inference position embedding or the range of the inference position embedding to the range of the pre-trained length. So for example, we can do a grouping operation, like we group every 2 position together and utilize the same relative position for them. So for example, 0, 0, 1, 1, 2, 2, 3, 3. So by doing this, we have the advantage and the disadvantage. The advantage of this method is that, so first, you can see the unseen position are disregarded. So the position, the relative position embedding of 5, 6, 7, they're gonna be mapped to 3. So 3 is within the range of the pre-trained length. So that will not cause the out of distribution issue. But the bad thing regarding or the disadvantage of this strategy is that they lose accurate information of the position embedding, right? So for example, in this way, the model cannot tell the relative word order of every 2 words. So for example, I love machine learning. The model cannot tell the difference between I love machine learning and I love learning machine. So this is the same to the model if we group every 2 position embedding together. But they can have a high-level idea of word distance. So for example, they can tell the difference between 0, 0 and 1, 1. So this is pretty similar to the bag of word in the traditional natural language processing. Okay, let's test how good it is of this very simple strategy. Okay, so here, x-axis is a serving context length, and y-axis is a perplexity in the log scale. So by the way, perplexity is a metric, the lower the better. So the lower means the model has stronger language modeling ability. So you can see if we test it on the original pre-trained length of 4,000, the model can have a really reasonable perplexity. But if you test on a sentence with 6,000, which is much longer than the pre-trained length, the model perplexity got really, really bad. So they basically cannot output any meaningful answers. So this is what happens if we group every two words together. So you can see if we group every two words together, we roughly enlarge the context length by 2 times. But after 8,000, the perplexity is still going up. That makes sense because after 8,000, we still have the out of distribution issue, right?
I have a quick question about
the
out of distribution thing. So your current assumption is basically the out of distribution only come from the precision encoding, right?
Yeah.
But I'm thinking about other possible causes for this. For example, let's say I try to give you a reasoning, you give me a question, and I try to give you an answer. I can give you a short answer without much reasoning. I can give you a very long answer with very detailed reasoning. So that probably is another type of auto distribution, and I think it's probably hard to just wrap around the precision encoding to make it work, right?
Yeah. I know the research you mentioned by you. This is actually referred to another research topic called, which is usually called length generation. Length generation. Length generalization in the field. So basically, you can think it like you train the model on reasoning data with like 8-step reasoning length, and then you test it on something like 20 reasoning length. So that's referred to another scenario. So, but here actually I mainly refer to the scenario that you got a length. So I try to so this is referred to the effective context length and the maximal context length. So here, you actually the problem mentioned by you is referred to the effective context length. So how model can leverage the information in their context. Here, the problem mentioned done in this research or in this paper is about how we enlarge the maximal context length. So here, I'm pretty confident that if we are talking about a maximal context length, so for example, what is a maximal length that model can generate a make sense answer that mainly rely on position embedding. But if so the problem mentioned by you is a much harder problem, length generation. This is beyond the scope of the talk.
I see.
Does that make sense?
Yeah.
I think we can actually generalize. We can actually generalize this simple grouping strategy, right? So previously we group every 2 words together, and now we can group every 8 words together. So by grouping every 8 words together, we increase the context length roughly by 8 times, right? But you can imagine the larger the group size, the more information loose we have. So you can see if we group every 8 words together, that means the model cannot distinguish the relative order every 8 words. Okay. So you can see there is actually a huge performance gap between this simple strategy and the original performance. So although we increase the effective context length by 8 times, but we sacrifice a lot of the model's language modeling ability. Later, I will talk about how we deal with this problem. So here, how we deal with the strategy we deal with this problem is again very simple. So imagine how we human process very long article or very long information. Imagine we are reading the book novel of Harry Potter. So for example, if we are reading at the chapter 7, right? So the most important thing for us to understand the current information of chapter 7 is probably chapter 4. It's probably chapter 6, and also the surrounding text of the chapter 6. Surrounding text of chapter 7. So that is because language we got locality. So, but for the long before context, so for example, the chapter 1, chapter 2, chapter 3, we can have, it is okay if we only got one vague impression regarding them, right? So because we human, we got a limited memory capacity in our brain. So here, our key idea is pretty similar to how we human process very long context. So we first do a grouping operation, like we previously introduced. We group every two positions together, and then we lose information. But here we can see we reintroduce the exact position of a local window. So that being said, all of the surrounding text of the current word, they are all exact. They are without any approximation. So here our key insight is that decent token, they are only responsible for understanding. So that being said, lousy position, they are good enough for us to have a vague impression. But the neighbor tokens, they are directly responsible for the next word prediction or next token prediction. So we should keep precise positions to make them capable of generating the final output. Okay, so by combining them together, we develop the method called self-extend, which can extending the context length without sacrificing the performance. So here we come to the evaluation part. So here this task is called needle in the haystack, which is a commonly used test for testing the long context ability. So this task is the concept of this task is very simple. So basically, they have a very long, irrelevant context, and insert one key information into this context. Like the best thing to do in San Francisco is eat a sandwich, and blah blah blah. And the question is only related to this key sentence. So what is the best thing to do in San Francisco? And the expected answer is something like eat a sandwich and sit in some park. So basically, you can see, in order to answer this question correctly, you only need to do a retrieval. You retrieve the correct sentence and answer the questions based on this context, based on this key sentence or the needle. Okay, so let's first take a look at what is the model performance of the original model or the vanilla model. So here, the model, if I remember correctly, is Llama 3. The Llama 3, they got 8,000 context. So you can see the model, also, by the way, green color means a pass, and red color means a failure. So you can see the model performance is really good when the needle is inserted within their maximal pre-trained length. So the performance is really good with at 8,000. But if you increase the serving length to, for example, all the way up to 100,000, the model fails. The model cannot retrieve the correct information. That being said, the models fail on this very simple task. But here, the upper figure is the one with our proposed method. So you can see we can very safely enlarge the context length to 32,000, and we can go all the way up to 100,000. But usually speaking, for this method, for this self-extended method, the longer the inference length, the more information we are losing because we are using a larger group size, right? So here, for example, I think the safe context length extended by our method is something like the 64,000. Actually, in my past experience regarding this method, so this method works really well if you enlarge the context length by 10 times. So usually speaking, if you use this method, enlarge your context length by 10 times, you won't lose. So at least on the majority of the benchmark, you won't lose anything. Okay, so here is another. So here is the commonly used long context benchmark data set. They are all from the a benchmark called the long bench. So we cover the scenario of single document QA, multi-document QA, fail shot learning, and coding scenario, which is all typical long context scenario. And here the model we use is Llama 7 billion chat, 4,000. 4,000 refer to the original context. Self-extend is our method. We use it to enlarge the context length by 4 times. And this method is called, if I remember correctly, this method is collect. So it is a fine-tuning the model on new collected data and to enlarge the context length. So here we can see our method is actually without any tuning. So we just replace our original attention implement, our original position embedding implementation with ours. Okay, so there is no actual training cost. But here we can see our method works really well compared to the fine-tuned one. So it can beat the fine-tuned one on majority of the benchmark, which is really. And the takeaway of this work is that, so usually speaking, self-extended, they can enable 10 times longer context without the tuning. And there's no need to collect high quality long context data, and there is no training cost. Second, this method has no harm on LLMs short context task performance. And the impact of this work is that this work is actually implemented in llama.cpp natural and also Keras NLP. If you guys are interested, you can scan the QR code to take a look at the report and also the code repo. And I have a few more words regarding this work. Okay, so like I previously mentioned, all these conclusion was built upon the case that you only increase the context length by 10 times. You can use this method to enlarge your context length by 100 times, but the performance is not guaranteed. So in practice, I suggest just use this method by 10 times. And so another thing I want to mention is that just like I previously mentioned, so this work was done in the area at the time Llama 2 was just released. Now we got Llama 3 and Llama 3.1. Llama 3.1 they got context length 128,000. You can still use this method to extend the context length of Llama 3.1 to 1 million. Okay, so the performance is still pretty good. Now we came to something related to the system support for doing the LLM inference. Okay, basically lowering the numerical precision to lower the inference cost. Okay, so first I will begin by introducing some background regarding the decoding process of transformer models. So at the beginning stage of each transformer layer, each word embedding X will pass to 3 different linear layers called query, K, and value layer to generate the query, K, and value embedding. But just like I previously analyzed, in practice during decoding stage, we commonly use a KV catch trick to reduce the recomputation. So you usually speaking in practice, query is a vector, and K and value, they are matrix. The query, they only contain the information of new token in this decoding step. And the K and value, they are storage the information of all previous context that the model should attend to. So let's take a look at a concrete example. So here, for example, the chill is the last new token to be last new generated token. And the previous context refer to it is a called monetarily failing it. Okay, so all information in the context, they are stored as one row in the K and value matrix. So actually one row in the K and value matrix, and this applies to all words in the context. And the query only contains the information about the last generated token chill. So once the generation process is finished, we add the K and value embedding of the last new token chill through the existing K and value catch. So we repeat this process until the generation process is finished, because large language model, they generate a new token one by one. And this streaming data structures is often called the KV cache in the inference community. So from our previous analysis, we can see that KV cache, they actually grow with respect to the number of tokens linearly. So that being said, if you increase the number of tokens by 10 times, then you grow the KV cache by 10 times. And also, actually in practice, or this is actually how ChatGPT, they serve millions of requests together. Okay, so ChatGPT, they have something like a scheduler. So for example, I ask ChatGPT one question. So some other users, they may ask ChatGPT questions simultaneously. So we first got a scheduler group different user requests together into a batch, and we feed this batch into the model to do the inference process. So actually, we rarely do single request inference because the cost is so high, because we need to amortize the model loading costs. This is what happens in practice. But you can imagine by increasing the batch size, we also increase the KV cache. So that's the reason why, if you take a look at the popular LLM serving system, they are all about dealing with KV cache, like VLLM, SGLong, and the decent serve, something like that. Okay, and why something is large is really bad is because they are not only the memory bottleneck, they are also the speed bottleneck. Because usually speaking, when hardware accelerator like GPU, when they do inference or computation, they need to repeatedly unload all the things they needed from off-chip memory to the on-chip memory. So here, off-chip memory refer to here the 80 gigabytes. Okay, so all your model weight is stored at here. On-chip memory refer to the static RAM, like SRAM. Actually, it is used by the register. So you can, from this profiling results, you can see if you got a super large KV cache or you got a super large model during the decoding process, almost the entire computation, actually almost the entire decoding time is taken by the data movement instead of the actual computation. Actually, so one more thing regarding the modern hardware is that actually the modern hardware like NVIDIA GPU from A100, H100 towards B100, their computation speed is super fast. Actually, their computation is even negligible when you compare the time spent on computation with respect to the data movement. Because data movement is really hard to do, because it's really hard to increase the memory bandwidth between different memory hierarchies. Okay, so usually speaking, in order to fully utilize GPU, you need to increase your workload to amortize the data loading cost. So by the way, this benchmark result is for decoding and with only one request. So you can see it is entirely memory bounded. Really bad. So one traditional way to reduce the I/O time is that we can reduce the total I/O volume. That being said, we can reduce the total bytes to be moved between different memory hierarchy. That refers to quantization. Okay, that's also the key reason why you see lots of the different serving framework and lots of the different quantization work for large language model, simply because they can reduce the I/O costs on model weights and also the KV cache. But today we will focus on KV cache. Okay, so this is for example, either K matrix or the value matrix. Each row is a token embedding, and each column refers to an embedding dimension. So originally, the KV cache is stored with using the floating point 16, this numerical precision. So that being said, every floating point number takes 16 bits to storage cost. So here, I will take 2-bit quantization as one example. Here, 2-bit, in 2-bit representation, we only got 4 different numbers from 0 to 3, because in 2-bit, we only have 4 different numbers. Okay, so in order to do so, the first thing we need to do is that we need to map the So because we only have from 0 to 3, we need to do a mapping of any of the original full precision matrix to the range of from 0 to 3. So in order to do this, we first need to do a scale. We need to scale the original floating point number to from 0 to 3, and then we do a bucketing. So for example, for different number fall into different bucket, we only use the bucket number to represent this number. This is a high level idea of quantization. Okay, it's conceptually very simple, but in my opinion, the hardest thing regarding quantization is how you implement them. But I will not talk about implementation in this talk. Okay, so from the algorithm side of quantization, the hardest challenge is that how you deal with outlier values. So outlier values frequently happens in large language model. So here, for example, imagine we got one outlier value 100 at this position. And this is how the data distribution looks like. So we can see we got a normal point that is far away from our normal point. And if we still utilize the same bucketing strategy for quantization, you will see all of the normal value, they will fall into the same bucket 0. And bucket 1 and bucket 2, they are completely empty. So that being said, you got a very low bit utility. So you can see after having these outliers, there is no difference between different word embedding. That's really bad. Model cannot tell the difference between the word like and the machine. You can imagine it, the output quality is definitely very low. Okay. So speaking of this, it is intrinsic to ask what is the outlier patterns in the K and value cache. Okay. Actually, in this work, we made a very interesting observation, and I think the impact is beyond the concept of quantization. Okay. So for the K cache, we observe that there is something referred to the outlier column or the outlier embedding dimension. So you see there are some outlier dimension that is consistently larger than all other normal embedding dimensions. See, so no matter what word you fit into it, some dimension they are the outlier dimension. This is really counterintuitive for the K cache. But on the other side, for the value cache, there is no obvious outlier patterns. Okay. So, oh, by the way, so I will not talk about why we have these outlier patterns in K cache. But if you guys are interested, I'm happy to discuss more on this thing. Actually, this phenomenon apply to all large language models that utilize relative position embedding. So again, it is related to the position embedding actually. Okay. So from this observation, our developed strategy is again very simple. We just quantize K cache alongside the embedding dimensions, and we quantize value cache alongside the token dimensions. So this is how K cache looks like. So for example, there are some outlier embedding dimensions or the outlier channels in the K cache. Okay. So our proposed strategy is that we do quantization of each column or each channel separately. So now you can see now different columns, they got their own scale and offset factors. So in this way, we disentangle the outlier columns with all other normal channels. But this method creates a new challenge because actually large language model do autoregressive generation, right? So the new token, they may arrive one by one, and the new token may exceed the original quantization range. So for example, you cannot utilize this scale and offset factor to represent this outlier value, -199. So to deal with this problem, we develop a very simple streaming data structure. So we first initialize an empty full precision buffer. And every time a new token is arrived, we just put this new token into this empty full precision buffer. Okay, so once this buffer is full, we do a quantization alongside the embedding column dimension. And after that, we concatenate the context buffer with the original with the previously context key catch, and we repeat this process again and again until the generation is finished. So for the value cache, for the ease of the implementation, we quantize value cache by token dimension. So every time a new token is arrived, we just quantize it to obtain the quantized value cache, and we concatenate it with the previously quantized value cache. Okay. So now we come to the evaluation. For the ease of presentation, we only show the two representative benchmark results. The first one is the long bench, which is again commonly used the long context scenario benchmark. So we can say even though we quantize the KV cache into 2-bit representation numbers, there is only very limited accuracy drop in this case. And the second data set is GSM8K. It is a commonly used mathematical reasoning. It is a relatively simple mathematical data set. So you can see, because this data set requires reasoning ability, you can see the accuracy drop is a little bit larger, roughly 2% of accuracy. So this is expected because every compression algorithm comes with consequences. So usually speaking, the harder the task you have, the larger the accuracy drop you have. So it's so that's being said, it's really important to have a very comprehensive benchmark for quantization algorithm. But thanks to the 2-bit quantization, we actually increase the throughput measured by the output token per second by 3.5 times. So that being said, it lower the inference. Roughly speaking, it's lowering the inference cost by 3.5 times. Okay. So impact of this work is that, so this is the first 2-bit quantization work with minimal accuracy drop. Oh, by the way, this applies to Llama 2. I believe that for Llama 3, 2-bit quantization, they sacrifice more on the accuracy. But actually, in fact, for the Llama 3 and all latest generation of model, any compression algorithm, they sacrifice more because there is much less redundancy in their parameters. So yeah, that's a very interesting observation actually. Second is that this work open source the 2-bit, 4-bit CUDA implementations for doing the quantization and also the quantized matrix multiplication. And this work has been used in the Hugging Face transformers to reduce your KV cache size. Okay, so if you guys are interested, again, scan the QR code to take a look at the technical report and also the code repo. And third one is some of my insight regarding comparing Mamba and transformers. Oh, by the way, how many of you guys have played with Mamba or heard about Mamba? Okay, yeah. So Mamba is actually, you can think it as another variant of recurrent neural network. So Mamba is first KV cache free. Mamba does not have any KV cache. Second, Mamba, they have linear complexity with respect to the number of tokens. So you can imagine the K scenario of Mamba is actually long context scenario. Because usually speaking, if your context length is short, so there is no difference between square quadratic complexity and linear complexity. So that's the reason why we want to have a benchmark against the Mamba here. So I know that the original Mamba paper is a little bit hard to read because it is a mix of lots of the mathematical details and also the details of high performance computing. But actually, if there is another way to understand Mamba, and it's really simple. You just take out the softmax from self-attention, okay? By taking out the softmax from the self-attention, then by the law, then you can change the order of the matrix multiplication. You can first calculate the outer production between K and V, then manipulate the results of outer production with Q. You can derive Mamba. So we can do it in a recursive way. Okay. Oh, by the way, this explanation can be found in this paper, which is really good. Okay, the gated linear attention transformers with hardware efficient training. Okay. Oh, by the way, I want to mention one more thing, is that actually this explanation is not very rigorous. I actually ignore the autoregressive maths, but here the key goal is for the ease of the apprentice and understanding, for you guys to have a quick high-level idea of MAMA, what a MAMA is doing. So here the ST here is the auto production I mentioned, the auto production between K and V. So here the memory pool is in size of D by D, not N by not like the attention matrix N by N. So here you can see the interesting thing regarding this auto production is that it is irrelevant to the size of the context. So for example, no matter you have 10 words or you have 10,000 words, the memory pool is still in the same shape. That's the reason why MAMA, they got constant complexity with respect to the number of tokens you have in your context. So if you think about auto production, MAMA is really like a token mixing mechanism. They mix different tokens together into this memory pool. And you also got one decay factor to forget past the context. This is also the same concept in the forgetting gate in the LSTM. Okay. So the memory pool refers to the compressed context through mixing tokens. And the key catch in transformers on the other side is uncompressed context through explicitly catching the K and V of all tokens. So here I will just talk about my key insight regarding comparing MAMA and transformer. Okay, so transformer on the one side, they explicitly calculating explicitly catching the all token information in your context. And MAMA is something like they do the token mixing and mix different tokens together. So this is my take regarding comparing them. MAMA is something like they first, if you ask it a question, so transformer, they are like doing the open-ended exam. So they have some material. So every time you ask it one question, the transformer, they can review the material it have and then answer the questions. But on the other side, MAMA is something like they are doing close-ended exam. So because MAMA, they explicitly mixing different material together. They are like, they first review all materials, first review all of the materials and get an impression in their brain. And they answer questions according to this impression in their brain. So this is how MAMA works. So you can imagine this MAMA related model is not that good at doing retrieval. Okay. So here is some comparison because we are a little bit out of time. So I can just show the quick results. So you can see this is again the retrieval needle in a haystack task. So we can see MAMA is relatively bad on the retrieval task. So the future, I think the one of the very important future direction regarding MAMA is that how we build a hybrid architecture. Because like I mentioned, MAMA itself, they got limited power on long context scenario, but we can mix them with transformer or full attention mechanism. So actually the hybrid model, they are super powerful. And some empirical work, they show that you don't need many transformer layers. Just one or two transformer layers is enough. All other layers, they can be MAMA or linear attention. Their performance is super good. Okay. So the future direction is that, so for example, how we deal with complex reasoning, because complex reasoning is one of the long context scenario. Second, how we build like different architecture, like hybrid model, how we mix MAMA layers or linear attention layers with full transformer layers. And third one is that how we do the evaluation of long generation, because long generation it's very hard to evaluate automatically, like the lengthy articles or the book knows how you decide whether the generated one is good or not. Okay, that's it.
Great. Thank you very much. So we probably have time for a couple questions. Any questions? Yes, Joseph.
So this might be an open question, but just want to like borrow a brain on the reasoning models.
Yes.
And this question has two parts. One is for the input, one is for the output tokens.
Yeah.
So in reasoning models, for the output part, it will generate a reasoning chain, right? But sometimes the correct answer has already been being revealed. But then the model, like one of the slides you show, let's verify it.
Yeah.
That's can be thought of as an overthinking problem, right?
Yes.
And my second question is related to the input token. So in my experience with like O1, O3, and R1, and also the distributed small model, it seems like all of them, whenever I use few shot prompting, or whenever I just have more information in the input tokens, they seem to degrade performance.
Yeah.
So do you have any?
Yeah, I can first answer the second question because I have a better idea regarding this one. I think the key reason why they did degrade the performance is that they are actually not instruction aligned. So all like I'm not familiar with O3 or O1, but I'm pretty confident that the DCL, the DeepSeek, and also the DeepSeek model, they are not instruction aligned. So they are base model. So they are not very good at instruction following. The more information you put into the context, they will easier to get lost. So back to your first question. Sorry, what was the first question again?
The first question is the overthinking in reasoning model.
Yeah. Very, very, very good questions. So my feeling is that actually this thing also mentioned in DeepSeek paper. So they mentioned that they just released the DCL model and the R1 and R10. They mentioned something like if you further do like DPO or you further do reinforcement learning to let them to learn how to answer the question, they can have a better performance. But for the open source, but for the sake of open source, they just release their base model. So that being said, this model is not very good at. They have lots. Actually, they have lots of the problem if you really play with them. They got overthinking. They got multilingual problem. They may suddenly change their language, and also they got, in my opinion, this very severe hallucination. And probably the reason is that they are not instruction aligned. But yeah, probably. So I think one possible solution to it is that we can do a DPO or to let them know which question they should think more and which question they should think less. Does that make sense?
Yeah. Thank you.
Okay. Other questions?
Quick question.
Yeah, go ahead.
Yeah, thanks for that talk. So, regarding the reasoning ability, I'm very interested in what could be the primary path to improve that. So I understand it could be related to, for example, the quality of the training data, the format of training data, the model architecture, and also the mechanism to incorporate feedback. And also for the evaluation itself, it's not entirely clear to me how to judge what is considered a high quality reasoning. So I just want to hear your opinion of what do you think is a primary factor we got to focus on to improve the reasoning capability.
Oh, okay.
And how they are interconnected. The factors are interconnected. Yeah, thank you.
Yeah, very good question. Speaking of this, I recently just to try to reproduce the aha moment of DeepSeek, and so my feeling is that so actually the high quality is very important for distill the knowledge. If you just do the reinforcement learning, there is no, in my opinion, there is no quality because during the reinforcement learning stage, you just feed the question to it, and all answer they are generated the model itself. So during the generation process, the model can get really the quality of the reasoning data, they can get better and better during the reinforcement learning stage. What is really important for this, the high quality data is very important for distillation. And in my opinion, you need to really got a very powerful reasoning model and let the reasoning very powerful reasoning model to generate the reasoning data, and then you do a data cleaning over the collected reasoning data to do the distillation. This is my opinion.
So overall, you think the data quality is most important, not the architecture or the way we format the data?
Very good question. So I think architecture, so the model size is really important, because when I do the reinforcement learning, I found that if you do it on a small model like 1.5 billion or 0.5 billion, it's really hard for them to have a aha moment, like mentioned in DeepSeek. And actually, DeepSeek, they also mentioned this work can only work well when your base model is strong. And so I don't know whether the number of parameters refer to the architecture you mentioned, but actually the model size is really important. This is the first thing. The format, I think, in my experiment, I have a format reward. So basically, I just do the regular expression check. So for example, whether they have the sync token, and whether they follow a specific format. If they follow, I give it a reward 1. Otherwise, I give it a reward 0. So during the training process, they learn to follow the format. So this is what I observed.
Okay, great. Yeah, thank you for sharing these thoughts. Very, very insightful. Thank you.
Okay. So we have a last question. Okay.
So you said like we can increase context leaks by 10 times and like with a sacrifice in accuracy.
Yeah.
So the best of my knowledge, like the largest context window we can afford right now is like 128,000.
Yes.
With the like open AI APIs and like. Is there a working model out there with like 1 million tokens?
I think Germany, they got something like 1 million or 2 million or even 10 million. I cannot remember the correct number, but Germany, they definitely got a longer context compared to 128.
From Google, right?
Yeah, from Google.
Okay. Thank you.
All right. So for the sake of time, I will have to close here, and let's thank Ray again.